Hello, and welcome to this presentation, Understanding Gain Compression and P1dB. In this presentation, we'll explain the fundamentals of gain compression and how gain compression is quantified using the 1 dB compression point, or P1dB. Gain compression and P1dB are closely related to third-order intercept. We'll cover this relationship only very briefly in this presentation, so please see the separate presentation, Understanding Third-Order Intercept, if you'd like a more comprehensive introduction to this topic. Gain compression is usually associated with amplifiers, so we'll start there. Most amplifiers have a so-called linear region, in which the amplifier increases the level of an input signal by a fixed amount. This increase, or gain, has units of dB. So if the input power is in units of dBm, the output power is simply the input power plus the gain. Plotting power out versus power in will usually produce a straight line with a slope of 1 over most of the amplifier's specified operating range. However, at some input power, the output power will no longer result in the same expected or linear output power. In other words, Pout becomes less than Pin plus G. The graph of Pout versus Pin begins to curve and flatten out, and at this point the amplifier is said to be compressed or in compression. Compression, therefore, can be described as the transition from linear to nonlinear operation. Although it normally applies to the behavior of active or powered devices, such as amplifiers, mixers, etc., compression can also occur in passive or non-powered devices. Operating a device in compression is almost always undesirable, primarily because it creates harmonics and intermodulation products. Instead of the output being simply a higher amplitude version of the input, compression can cause the output signal to become distorted. It's therefore important to have a way of defining or quantifying the power level, or point, at which compression, and thus distortion, begins to occur. The standard way of quantifying compression is using the 1 dB compression point, usually abbreviated P1dB. P1dB is the point at which the output power is 1 dB less than the expected linear value in dBm. Another way of saying this is that P1dB is the point at which there is 1 dB deviation from the expected linear gain. P1dB can therefore be considered as the boundary between a device's linear and nonlinear regions. It's important to keep in mind that P1dB can refer to either the output power level at which compression occurs, or the input power level at which compression occurs. Note that output P1dB is simply input P1dB plus gain minus 1, since output power in compression will be 1 dB less than input power plus gain. This plot of output power as a function of input power is the classical way of describing or explaining compression and P1dB. However, we can also plot gain as a function of input power. In this case, we would get a horizontal line that curves downwards when compression occurs. Determining the point at which this straight line droops or falls by 1 dB gives us the input 1 dB compression point. This graph of gain versus input power is commonly used when plotting measured values and when calculating P1dB, in part because it makes it easier to visualize the decrease in gain that occurs as a device goes into compression. As mentioned earlier, P1dB is a very important specification for amplifiers and many other devices. A higher value of P1dB means greater device linearity and a greater operating range. Recall that for linear behavior, devices should be operated well below P1dB, and this is especially important with non-constant amplitude signals, such as those used in cellular or Wi-Fi. Operating well below P1dB is, however, inefficient, but this inefficiency can be reduced by using a device with a higher P1dB. It's also important to keep in mind that P1dB is a convention. There's nothing special or magical about gain decreasing by precisely 1 dB. Measurable distortion can occur before, at, or beyond P1dB. Therefore, you may sometimes see compression specified for other dB values in certain applications. For example, high-power amplifiers may be specified using a 2 or 3 dB compression point. And some devices, such as voltage-variable attenuators, are often specified using a 0.25 dB compression point. However, P1dB is by far the most common compression point, and is used for the vast majority of active devices. Before we move on to how P1dB is measured, let's pause for a moment to discuss third-order intercept, which is another common way of quantifying linearity. Very briefly, third-order intercept involves the relationship between the level of a signal and the level of one of its third-order intermodulation products. Third-order products are additional signals produced by a device operating in its nonlinear region. As we can see from this graph, compression prevents these two signals from meeting, but the point at which they would meet is called the third-order intercept point, abbreviated IP3 or sometimes TOI. Like a higher P1dB, a higher IP3 indicates greater device linearity. Various formulas or rules of thumb exist for estimating IP3 from P1dB or vice versa, and in most cases, the P1dB of an amplifier will be somewhere between 10 and 15 dB lower than IP3. Although IP3 is a very important linearity measurement, we won't go into any additional detail on it in this presentation, so please see the separate presentation, Understanding Third-Order Intercept, if you'd like to learn more about this topic. Next, let's talk about measuring P1dB. Measuring P1dB requires an RF source at the input of the DUT and an instrument that can measure the output power of the DUT. The test signal is normally a CW or constant amplitude signal, and the signal is then swept or stepped over a range of powers. The results are recorded and plotted to determine P1dB. Although this procedure can be done by hand, automation is desirable since this dramatically increases measurement speed and helps to avoid user error. If needed, calibration can also be performed to remove the effect of cables, connectors, etc. in the test setup. Depending on the gain of the device under test and the measuring instrument, it may be necessary to add an attenuator to the DUT output. This attenuator both helps to avoid creating compression in the measuring instrument and helps prevent the measuring instrument from being damaged or destroyed. And finally, if the DUT source doesn't natively have enough output power to push the DUT into compression, a preamplifier might be needed at the DUT input. But care should be taken to ensure that any amplifier added to the test setup is operated well below its own compression point. With regards to measuring instruments, either RF power sensors or spectrum analyzers can be used to measure the output power of the device under test. But in both of these cases, a separate signal generator is needed to create the input signal. Another very common way to measure P1dB is using a vector network analyzer or VNA. Since a VNA can both generate and measure signals, no external signal generator is needed. In the remainder of this presentation, we'll briefly explain how each of these instruments can be used to measure P1dB. RF power sensors are a simple and cost-effective way of measuring gain compression and P1dB. In this scenario, a basic RF signal generator provides the input signal P in, and a sensor connected to the output of the device under test measures the output power P out. An advantage of this approach is that many RF power sensors provide highly accurate measurement results. These results can be obtained and plotted in two ways. The first is a purely manual process, by which the user records and plots P in and P out while stepping through an input power range. A faster and more sophisticated way of doing this is programmatically. That is, by using a simple program, that controls the signal generator output, queries the sensor for measured power, and then creates the gain curve plot for calculating P1dB. A similar methodology uses a signal generator and a spectrum analyzer. Here again, the generator provides the input power, and the analyzer measures the output power. And as before, the configuration and measurements can be done manually or programmatically. Note that some spectrum analyzers have a specialized application for making amplifier measurements. In this case, the spectrum analyzer directly controls the signal generator, usually over a LAN connection. The results are automatically calculated and plotted on the spectrum analyzer itself, eliminating the need for a user-created program running on a separate PC. The third method involves using a vector network analyzer or VNA. Because VNAs can both source P in and measure P out, this approach does not require an external RF signal generator. In fact, gain compression and P1dB measurements are a standard measurement on many vector network analyzers. Although the majority of VNA measurements involve sweeping over a frequency range using a fixed power, in gain compression measurements, the frequency is normally fixed, and the VNA instead sweeps over a power range. Most VNAs support a procedure called power calibration, which improves the accuracy of both generated and measured power levels. This calibration can also be used to reduce or remove the effect of the test setup, including any attached cables, connectors, etc. Let's end with a brief summary. P1dB, or the 1 dB compression point, is often used to quantify the gain compression and linearity of many types of devices, particularly active devices such as amplifiers. P1dB is the point at which a device's measured output power is 1 dB less than the expected linear output power. Higher values of P1dB are desirable because beyond this point, devices are operating in compression, which creates distortion in the form of harmonics and intermodulation products. P1dB is determined by measuring the input and output power of a device, and then plotting gain as a function of input power. Several different test and measurement instruments can be used to plot gain curves and calculate P1dB. One method is using signal generators with either RF power sensors or spectrum analyzers. Another method is using a vector network analyzer, or VNA, which both supplies P in and measures P out. This concludes our presentation, Understanding Gain Compression and P1dB. If you'd like to learn more about linearity measurements, compression, or measuring instruments from Rohde and Schwarz, please see the links in the video description. Thanks for watching.